Welcome everyone to Living Systems 1. This is a core subject for students studying the Bachelor of Agriculture and Technology, regardless of your major. You may be studying this degree hoping to major in aquaculture, or viticulture and winemaking, agriculture, or agronomy. Some students decide not to major and will instead study this degree as a general degree, which means that they can choose subjects from any of the major specific areas. The subject codes, as shown on this slide, are different depending on whether you're a La Trobe student, in which case the subject code for Living Systems is Sci1 LS1. If you are an international student or you're studying the Bachelor of Equine Studies, the subject code is BS 109. My name is Silvana Iaconi and I'm always excited to welcome the new students into this subject. So let's start with a timetable. So this timetable shows the schedule for both face-to-face students and for blended delivery, in other words, online students. But we use the term blended delivery instead of online for two reasons. One, because it's not 100% online, and two, because blended delivery is the term that's used by La Trobe University. So we need to be compliant in that way. All right, now let's start with face-to-face delivery. And the reason that this might be useful to the blended delivery students is because sometimes in the past, blended delivery students decide to switch between the two delivery modes. They might do a few weeks online and then they might have a Monday spare where they decide, I might actually go into class and see what it's like. Okay, so let's look at our Living Systems timetable. Living Systems always runs on a Monday with lectures from 9 until 11 a.m. in Building L, room L127. Then we have a break. Then from 12 until 1 p.m. We have a tutorial in the same room. Then from 1:15 to 3:15 p.m, students will go to the lab for their practical class, and this commences from next week. So there were no lab classes today. And the lab is in the same building, Building L, room L109. Then starting from next week, I run an optional student support class from 3:30 to 4:30. And also, this is also in L127. Now, this is for students that might not feel comfortable with certain concepts that they're learning. They might be struggling a little bit with one of the formulas or anything at all. So this class is really structured and driven by the students that attend. They tell me what they need help with. They might need a little bit of help with structuring a prac report, or they might need some help with some of the tutorial exercises and so on. But having said that, don't feel that you need to attend this class to get help, particularly for the blended delivery students. For you guys, it's really important that you keep in close contact with me by email or by phone and just ask any little question that you have, okay, rather than just letting things slide. So that's face-to-face delivery. To the right here, we have our online class for blended delivery students. It runs every Monday evening from 6:30 until 8:30 p.m. Sometimes we'll finish a little bit earlier, just depends on the lectures for that particular week. Okay, requirements for this subject. The most important requirement is a lab coat. This is something that you must purchase if you don't have one already from previous studies. Lab coats are mandatory in lab classes, and you can visit the La Trobe University Co-op bookshop in Bundoora and purchase your lab coat directly from there at a cost of about $28. Or you might prefer the convenience of ordering online, which you can do via Live, Work and Playware, which is in Whittlesea. If you follow this link, you'll be able to order a lab coat for $36, and even though this is more expensive, they deliver the lab coat directly to me, so that when you start your prac classes, which will be later in semester, then the lab coat will be there for you. Now, keep in mind also that you don't just need a lab coat for living systems. There are other subjects that include practical components where you'll be required to wear lab coats. Now, some students are not very good at remembering to bring their lab coats when required. So these students can actually hire a lab coat from me, and that'll cost $3 plus their student card until that lab coat's returned. All right, also required for lab classes, completely closed shoes. So obviously no thongs, sandals, shoes must completely enclose the top part of your foot. You will need in a few weeks' time a scientific calculator, so just a basic scientific calculator. If you already have a graphics calculator from school or from other studies, that's fine. But keep in mind that you would have to clear the memory for the final exam. Okay, your normal paper, pens, pencils and so on. Prac manual. The prac manual will be provided for you when you start prac classes, but I will be posting a copy of the prac manual on Moodle so that students can actually start looking at the pracs that they're going to undertake during the prac workshop. And I'll come back to the prac workshop in just a minute. Okay, fine tip permanent marker, the type that you would buy from the newsagent. This can be very useful in prac class for labelling glassware, microscope slides and so on. And I always say to students with long hair, keep a hair tie in your pocket, in your bag, in your car, wherever, because in prac classes, long hair must be tied back. We've only had one student whose hair caught on fire during a prac class, but I certainly wouldn't want to see that again. And keep in mind that student actually did have their hair tied back, but their hair was so long, they had so much hair, as they sort of turned around, their hair, the bottom of their hair caught fire on the in the Bunsen burner flame. So not something that you can easily predict will happen. And of course they were fine. No harm done, they were just very embarrassed. All right, textbooks for living systems. There are two prescribed textbooks for this subject, a chemistry textbook called Principles of General Organic and Biological Chemistry by J.G. Smith, and a biology textbook called Biology and Australian Focus. Now, both of these textbooks will cover all the chemistry, biochemistry and biology that we'll study in both Living Systems 1 in first semester and Living Systems 2 in second semester. But the question that you want answered is, do you have to buy these very expensive textbooks? And the answer is not that simple. It really depends on your background in chemistry and biology. So have any of you guys ever done chemistry before or biology, say at year 11 or 12 level in secondary school, or as part of another course of study that you did elsewhere?
I did biology and chemistry to grade 12, but
oh, did you, Liz?
That's 25 years ago.
Oh, 25 years ago, okay. All right, that's fine. Okay, year 11, was that chemistry or biology? Only chemistry, year 11, long time, chem, okay. All right, no problem. That's fine, because most students that actually enrol in this course, most students don't have any prior chemistry, which means that we actually start the chemistry from scratch. So if you've done a little bit of chemistry before, it's a really good revision, really good refresher for you. Most of the students have studied biology, at least in year 11 or both year 11 and 12, but some students don't have any prior studies in biology. So for that reason, I'll start the biology from scratch too. Okay, so textbooks. Do you need to buy the textbooks? You don't have to buy them. I never say to the students, refer to this chapter or answer these questions in the textbook. I do try to provide you with all the information that you need in my lecture notes, tutorial exercises, and so on. And what I suggest to students is that they visit, if possible, visit our library at Epping, because there are a couple of copies of this chemistry textbook and older editions rather, and a couple of copies of the biology textbook, but older editions. And you can borrow those, or if they're already gone, you can borrow other biology and chemistry textbooks. There's a whole range there by different authors, and any one of those will cover the same type of material. So, you know, think about it, the fundamentals of chemistry and biology don't really change a lot over time, particularly in the textbooks. It takes a long time for them to be updated. Otherwise, you can search online for an older edition of either of these textbooks and see if you can pick it up cheap. If you think that you will need, fantastic, there you go. Thank you for that. $25 to $50, Gumtree. Fantastic, there you go. So that's the way to go to save yourself lots of money. I think the chemistry textbook, last time I checked, was nearly $200 brand new. And the biology textbook, maybe it's $150 or so brand new. But anyway, textbooks are very expensive. So if you really want one, and they are very useful to have, these are fantastic textbooks. And the chemistry one in particular, I selected this one as a prescribed text because it's really suitable for first year degree students who have no prior chemistry. It's not one of those typical hardcore chemistry textbooks that are designed for students that are going to go on and major in chemistry. Okay, no one in this course is going on to major in chemistry. You're only studying basically the fundamentals that are required to go into other subjects. All right, so that's it on textbooks. So I'll leave that up to you. And as I said, if you find a really old edition of the biology textbook, that will be fine. More than okay. All right, availability of subject material. Every week, I will open up the following week of lecture notes. So you can actually look at them in advance, and they will be on Moodle. Moodle is our learning management system, online learning management system, often referred to as our LMS. All right, weekly tutorial exercises will also be available on Moodle, and we'll come back to those later. Prac books will be provided to you. Face-to-face students will receive their prac books next week because they start prac classes next week. Blended delivery students obviously don't do their prac workshop until later in semester. I'll come back to that. That's when you will receive your prac books. All right, virtual classroom recordings. So all these evening classes are recorded, and I normally post the recording on Moodle the following day. So sometime tomorrow, this recording will be available. So if you can't make it one Monday evening, then at least you can actually view that recording at any time. Sometimes I provide actual lecture recordings that I will ask you to actually listen to before you come to the Monday evening class. And then we'll do something a bit different, like work our way through tutorial exercises, or towards the end of semester, we'll start doing revision instead of going through the lecture material. But I'll let you know as that happens. Okay, if you need help, then definitely ask me either Monday evening, during the actual class, after the class. I'm happy to stay behind and help you out. Send me an email at any time. Call me. All my contact details are on the subject outline. So you can actually call me, leave a message. I'll call you back if I'm busy teaching and not in my office. If you're ever on campus, then come past my office for a chat, Building A, room A130A. If you've already been to the course coordinator's office, that is Nikki Cooley, my office is right next door to hers. Okay, if you're ever around Epping and you wanted to drop into the student support class, feel free. If there are any problems with pracs or you need help with any of the prac exercises, talk to your prac supervisor. She's very experienced. She's been demonstrating pracs for many years at both Melbourne Polytechnic and at La Trobe University. All right, class rules don't really apply to us during our online class. All right, transition to higher ed. Now, this is mostly for school leavers, which we only actually have a few in the course that are straight from school into this bachelor degree. But I'll go through some of these points here because they're relevant to everyone, whether you studied, last time you studied was 25 years ago or 2 years ago. So in secondary school, they provide guided homework tasks to assist student learning. In higher ed, your learning really depends on you being able to manage your time and revise the subject material during semester. In other words, you need to manage your study time. It's all about independent learning. You won't have any of your lecturers breathing down the back of your neck or saying, where's this assessment and where's that assessment? It's really all driven by you. In secondary school, study tasks are fairly evenly spread throughout the year. This definitely doesn't apply in higher ed. You will have many assessments due at the same time towards the end of semester. So what this means, and we all tell students this every year, as soon as you know what to do for a particular assessment, do it straight away. Work on it straight away, get that one out of the way. Because what happens every year is that some students will just let the assessments pile up, they put them off, and then they get to the end of semester and suddenly they just have too much and it's impossible to do everything. So what happens? They fail to submit all the assessments, there's 0 right there, or they do manage to submit the assessments but they're very, very stressed, they're missing classes, and they submit really poor quality work. Okay, so this is a really important point for everyone. Secondary school, there are many opportunities for feedback and assistance. Now, normally this is not the case in higher ed. If you go to any of the big universities, there are just too many students. And of course, the lecturers don't even get to know students' names, let alone provide that one-on-one. That's not the case with us. We have small classes, and we're happy to go out of our way to give you feedback and give you extra assistance if required. Secondary school, what else is relevant here? All right, secondary school, there's less emphasis on exams for assessment. Now, in the past, there was a lot of emphasis on final exams in higher ed. In fact, for many subjects, most of your mark for a particular subject would actually come from your final exam or final exams. That's changing a lot, has been changing quite a lot over the last 10 years. And now you'll find that for some of your subjects, there are no final exams at all. For living systems, there is a final exam still, but be aware that when you have subjects without final exams, that generally means that you have more assignments during semester. Okay, so that increases the pressure on you in that way, and of course makes it even more important that you keep up with the assessments. In secondary school, there are more frequent tests and exams that cover smaller amounts of material. In higher ed, there are definitely less frequent exams, and those exams can cover very large amounts of material. In fact, you may have the odd final exam that will cover the entire semester of lecture material. That's not quite the case in Living Systems, but we'll talk about that in just a sec. All right, as I said earlier, there's a very important document on Moodle, which I'd like you to carefully read over. It's called the subject outline. You'll get a subject outline for each subject that you're enrolled in. And this is only a small part of the subject outline, what I'm showing you here. So in the subject outline, you'll get all the information regarding assessments and due dates and prescribed textbooks, recommended textbooks, and the policies and so on and so on. All right, I've just pulled out the schedule here for Living Systems just to point out some important points for you. All right, so let's start with this column on the left, week numbers. So the semester is divided into 13 weeks in total. Only 7 weeks are shown here. So we're obviously here in week 1. Then you'll be given the topics here. The lectures will correspond to chapters in the relevant textbook. And I try not to stray very far at all from the material in the textbook, so it makes it easy for students to actually go back to the textbook and read more about the topic if they need to. Then on the right here, you'll have due dates for assessments. All right, so let's go through these weeks. Week 1, 2, 3, 4. Now, this is the one that I wanted to point out. Week 4, 12th of March, Monday the 12th of March. This is Labor Day public holiday. So there are no face-to-face classes on this day, but we will still have an online class. Okay, week 5, week 6, and then note we have a mid-semester break. So you'll have a week off. This is not given a week number, this week off. Now, I shouldn't say that you have a week off. This week is a break from attending classes, but what students should be doing during this time is catching up with any work, revising, working on assessments, and so on. So that's an important week, which occurs after week 7. Then we go into week 7 after the break. And at the end of week 7, you'll see here details of the prac workshop. So for students that are taking this subject by blended or online delivery, you must attend this prac workshop and complete all the pracs within the prac workshop in order to satisfy the practical requirements for this subject. Here's the prac workshop dates: Saturday and Sunday, 14th and 15th of April from 9 till 6. We normally finish a bit earlier, but I always say 6 o'clock just to cover ourselves. All right, where do the pracs take place? Melbourne Polytechnic in Epping, Building L, room L109 will be the venue. So this is the lab in Building L. Okay, so will that be a problem for anyone to attend that prac workshop? So you can just say all good or problem, because I'm going to sign you up for the prac workshop, if that's okay. All right, so you're good. Prac workshop. So I'm just putting your names down. Oh, you may still be in Harvest. Okay. So you're on Vintage at the moment. Okay, that might be a problem. All right, I'll need to talk to you about that later on. All good for you. Kicking off tomorrow. Okay. All right, we need to have a chat about that too. Yes, you will need your lab coat before that prac workshop. Okay, not before. No, not before that. But that's when, if you're intending to do the 2-day prac workshop, yeah, absolutely, absolutely. Give me a call tomorrow. If I don't pick up, just leave a message with, say, your mobile number and I can call you back. Okay. All right, so I'll just get your names down now. All right, terrific. All right, thank you. All right, so that's in week 7. Now let's go to week 8. 9, 10, 11, 12, 13. So we finish in week 13. Some subjects have moved to a 12-week semester to keep in line with La Trobe's semester. I'm still running 13 weeks. So after the 13 weeks, you'll have a 1-week study period, as you can see down here, and then we enter the 3-week examination period. The exam timetable is normally released around the middle of semester, so don't book any overseas holidays just yet until you know when the exams are. Normally, Living Systems final exam is in the first week of this 3-week examination period, normally in the first week. In fact, most of the exams are normally scheduled in the first week of that period. Okay, but don't book anything just yet until you actually see your exam timetable. All right, let's run through the assessments now for Living Systems. You will write 2 lab reports based on 2 practical classes, 2 pracs. One report, you can choose any prac on which to write that report. And the second report, you will have to write the report on a specific prac called acids and bases. But we'll talk more about that later on. Okay, the length of the report, 500 words each. They are due for weekly prac students. Report number 1 is due in week 7 of semester. Report number 2 is due in week 13, so the last week of semester. Note the times, they are due by 9:15 a.m. So, of course, we need to draw the line somewhere in terms of deadlines. And so any report or any assessment that comes in after that time, penalties will start to apply, 5% for every day late or part thereof. Now, for students that are doing the 2-day prac workshop, both reports, 1 and number 2, are due in the last week of semester, on the Friday of the last week by 5 p.m. All right, having said that, once you've actually completed the prac workshop at the end of week 7, my recommendation is always for students to start on one of those reports immediately. That is, once you've recovered from that weekend, because it's quite tiring, very intensive. Start on the first report straight away, and then what you can do is that you can email it to me as a draft and ask me for some feedback. If I receive a report draft earlier than 1 week before submission date, I'm happy to give you feedback so that you can apply some corrections and improve it before you actually submit it. And then, of course, that really helps you and guides you in writing that second report. So give yourself plenty of time there. All right, weighting. Each report is worth 10% for a total of 20. Tutorial exercises. Every week I'm going to provide you with a set of tutorial exercises based on the lectures for that week. But only 6 sets of tutorial questions are actually assessed. And these are actually submitted by completing an online quiz, which you'll find on Moodle. So let me explain this again. The tutorial exercises for a given week, I provide a hard copy of those questions. That is, you'll see the tutorial questions for this week already on Moodle. So you can work your way through those questions, and then when you're done, get onto the online quiz, and the same questions will be found in the online quiz. And then you can answer them via that quiz, and you'll get immediate feedback on the questions as to whether you're right or wrong. Once you've finished the first attempt at the quiz, you can go back and start again and have a second attempt. Okay. Another thing to keep in mind when it comes to the multiple choice questions that you answer, when you go onto the online quiz, the answers, the possible answers to each multiple choice question will actually shuffle around. They might not be in the same order, that you see on your hard copy of the tutorial questions. Okay, so keep that in mind also. And each set of questions is worth 4 or 5% for a total weighting of 25%. Now, what often happens is that students are very good at completing the assessed questions and submitting their answers through the online quiz. But when it comes to the non-assessed tutorial questions, everyone tends to let them slide. And I understand that because you've got assessments, other assignments that are assessed that you need to be working on. But keep in mind that the non-assessed tutorial questions are also very important for preparing for your mid-semester and final semester exam, because many of those questions will resurface in the exams, either in the same format or slightly modified. So they're all equally important. So I really recommend that you do all the tutorial questions. That brings me to the mid-semester exam. This is an online exam, so students generally do very well because, of course, it's open book. You do it from home, and it's based only on weeks 1 to 5 of subject material. In other words, lectures 1 to 6. The mid-semester exam will open during week 8, and it will be open for 2 days. So from 6 a.m. on Sunday the 22nd of April, and it will close at 11 p.m. the following evening. So you can start this exam at any time during these 2 days. But once you start, you'll have 1.5 hours to complete the exam. Okay, weighting for the mid-semester exam is 25%. So that's an easy one. Easy one, if you've done all the work up until then, you won't have any problems with this. Then we have the final exam. The final exam is not an open book exam, it's closed book. So this is a little bit tougher. It is based on the subject material presented from weeks 6 to weeks 13. So the first 5 weeks of lecture material is not re-examined in that final exam. Duration 1.5 hours, weighting 30%. Now, as I said to the students this morning, it's really critical that you submit all the work, even if it's a 4% set of tutorial questions. Don't let it slide, submit everything. If you do, then there is a pretty reasonable chance that by the time you actually hit the final exam, you might already be sitting on 50% or nearly 50%. And 50% is the pass mark for this subject. So that's a really nice place to be going into that final exam, knowing that, hey, I've already passed the subject or I've nearly passed the subject. It takes a lot of pressure off you going into the exam, and also knowing that whatever mark you get on that final exam will just boost your mark to a higher final grade. All right, so please submit all your assessments. Okay, we have a question here. Oh, sorry, just move that out. Do all assessments need to have a pass? No, they don't. No, they don't. So when it comes to the prac reports, the tutorial exercises, the mid-semester exam, or even the final exam, there's actually no such thing as, even though it's marked in that way, there's no such thing as really a pass or fail. Whatever mark you get, whether it's 80% or 30%, that still accumulates towards your final mark. Okay, so there's no requirement to actually get greater than 50% or 70% on a particular assessment, which is good, which is handy. Not that I'm suggesting that you only get 20% on each assessment, which brings me to a really important statistic. Living Systems has been running for 8 years. This is year number 9, and in every year that it's run, there have been some students that fail the subject. That's just a given for subjects that include chemistry, biology, physics, maths, any of those sort of hard sciences. there's always students that fail. Now, if we think about all those students that have failed over the 8 years, only one of those students actually submitted all the work and still failed. Only one. All the rest of those students that failed to submit assignments or assessment pieces, which is really, really frustrating, or must be very frustrating for those students when they realise that if they had submitted one more set of tutorial questions and just got 50% for them, they could have passed the subject and avoided repeating the subject and paying all that extra money. So let this be the first year that everyone passes. Everyone submits everything and everyone passes. That would be really awesome. Okay, so really important. Regardless of what the assessment's worth, submit it. Even if you just happen to get to it last minute and do a really ordinary job, get it in anyway. Because it's really not very pleasant to get a final mark of 48% and you failed the subject and there's no recourse. Okay, prac class attendance. Students that are doing weekly prac classes must attend 80% of all pracs. In other words, they can miss 2 pracs and still satisfy the practical requirement for the subject. Students that are doing the 2-day prac workshop must attend and complete all the pracs scheduled on those 2 days, because those pracs represent only 80% of all the pracs for the subject. Okay, so this is really the only mandatory component of the subject, to attend and complete the prac classes. All right, so why do we need to study chemistry and biology? Considering that we have students that are studying aquaculture, viticulture and winemaking, agronomy, agriculture, equine. I also teach a modified form of this subject to Bachelor of Veterinary Nursing students. So let's think about why you guys need chemistry and biology. All right, and we have some important clues here. So when we think about soils, there is a component in one subject that everyone does, and it's about soil science. To really understand soil science, you have to have some fundamentals of chemistry. Plant physiology. This is a core subject for viticulture and winemaking students and agronomy and agriculture students in 2nd year. To understand any physiological process, whether it's in plants or whether it's in animals, you must understand some underlying chemistry. Environmental studies, nutrition, the list goes on and on. So what you'll find is that even though we'll cover some concepts and you won't be able to see how it's relevant, at this point in time, you'll get to your other major specific subjects over the next 3 years and you'll say, oh, that's why I learnt that in living systems. So these concepts will come up again and again. An important one for viticulture and winemaking students, in 2nd year, you have to take the subject Wine Chemistry 1. And every student that's ever done Wine Chemistry 1 has said, Living Systems 1 and Living Systems 2 chemistry, it's a must going into Wine Chemistry 1. Some of you might even elect to do Wine Chemistry 2 in 2nd year, 2nd semester, but that's an elective subject. So that's up to you. So super important for everyone, but particularly for viticulture and winemaking students. Okay. Next question, why do we combine chemistry and biology into the one subject? In probably every university, they still teach chemistry as a very separate standalone subject, and that's taught by academics from the chemistry department. Biology is taught separately and it's taught by various academics in the life sciences, whether it's academics from ecology, botany, zoology, and so on. And each department is very, very protective over their own domain of chemistry or biology. But the decision was made many years ago at Melbourne Polytechnic to actually try combining them, combining them into the same subjects so that we could better show that relationship or show those links between the chemistry and the biological processes. And I have to admit, I was sceptical at first because I came on board when chemistry and biology were still taught as separate subjects. But by the time the first year was finished, I was convinced that this is the way to go. It's much, much easier to teach the chemistry and then teach the biology and show those links, show where the chemistry comes into the biological processes. Because after all, biological processes and biological systems are often driven by underlying chemical reactions. So to have a really good understanding of biological processes, you need to know a bit of chemistry. And here are some examples for you. Does anyone recognise this structure down here? This is a structure that you'll find in most plant cells and most animal cells. Does anyone recognise this? If you've done biology, then you might recognise it. No? Anyone else? You can just say yes or no. No. Okay, this is a structure. This is a structure. It's close. It's actually part of a cell. So this here, this little structure here, this is a cell, and that little brown structure that you can see in there is what's shown here. This is called a mitochondria, or I should say mitochondrion for singular. Structure found inside plant cells and animal cells. Oh, you can't see the whole picture. Can you not see this part here? Only half. Okay, that's interesting. What about everyone else? Can you see these images at the bottom of screen here? You can? Yep. You can. All right. So there's something about your computer that's not allowing you to see that image. All right. I'll need to think about that one. Okay, great. Yeah, please let me know how you go with that. All right, mitochondrion. So this is found inside plant and animal cells, and in here, within the mitochondrion, this is where sugars and fats are actually chemically altered to generate energy that drives all cellular processes. But to understand the process that occurs in here, you need to understand a bit of chemistry. So in just pure biology, you will learn about this structure and you will learn about the function. But to really understand the process, you need to have some of the chemistry. And this is where a subject like this can combine those processes. Here's another example. Who recognises this one? This is another structure that's found within cells, but only in plant cells and algae. Only plant and algae cells contain this structure. And here's a clue for you. Light energy hits these structures. Any idea? If you've got no idea, just write no. No. Exactly right. Photosynthesis. This is a structure called a chloroplast, which is found in plant cells and algal cells, and this is where the process of photosynthesis takes place. You must know some chemistry to understand photosynthesis, and that's something that we'll go into in a lot more detail in second semester. Okay, so photosynthesis. Keep in mind also, of course, plants and algae photosynthesize. There's also a group of bacteria that photosynthesize, but bacteria do not contain these structures, these chloroplast structures. All right, the last example here. Have a look at this structure here, just this part here at the top. And if you've never done any chemistry before, or even biochemistry, you'll look at that and say, I have no idea what that's all about. Is that how you're feeling at the moment? You have no idea what the letters mean. You have no idea what these lines indicate. Single lines, double lines. Basic idea, okay? You've got a basic idea. Okay, so if you've done a bit of chemistry or biochemistry, or I can tell you by the end of the year, you'll know exactly what that is. You'll look at that and say, that's easy. I can explain that without any problems whatsoever. And what we're actually looking at here, just this structure here at the top, this is called an amino acid. And amino acids are the basic building blocks of proteins. This is just one particular type of amino acid. Oh, sorry, just a general representation of an amino acid, not a specific type. Okay, so once again, we're talking about biological molecules such as proteins, but to understand them, you need that underlying chemistry, as you can see from looking at this. All right, and that brings us to our first lecture. So who has any questions for me before we have a quick break and then get on to the lecture? Any questions whatsoever? Not yet? Okay. I have a feeling that that questions will be coming. All good? All right, terrific. All right, let's have a quick break. Would you like 5 minutes, 10 minutes? That's up to you. 5? 5? All right, let's break for 5 minutes. I will see you at 7:30. All right, let's start with lecture 1, matter and measurement. Is the audio still good? Still clear? Excellent. Okay, so in this lecture, we're going to cover lots of different concepts. It's really just an introductory lecture. Some of the concepts are traditionally covered in chemistry, and I still like to cover them, but they might not be that important moving forward. Other concepts, and I will stress this, are important going further into later lectures where we might expand on the concepts, or they're important going forward into other subjects. But I'll certainly let you know as we move through this lecture. So let's start by defining chemistry. What is chemistry? It's a study of matter, its composition, its properties, and how substances transform from one substance into another. So what is matter? Matter is anything that has mass and takes up volume, and we'll come back to that term mass a little bit later. Of course, we can have naturally occurring matter, such as cotton, sand, or we can have synthetic man-made matter, nylon, styrofoam, and so on. All right, our first concept relates to the most common states of matter. And this is something that everyone learns in secondary school. And actually, they're even teaching this now in late primary school years. The 3 most common states of matter are solid, liquid, and solids, liquids, and gases. So let's just look briefly at the properties of each. So a solid has a definite volume. If you place a solid into a container, the solid will maintain its shape regardless of the container. A solid has particles that lie close together in a regular 3-dimensional array, and we can see this here. These are all the particles within a solid, and you can see that they're packed tightly together and they're very ordered in this 3-dimensional pattern. So let's compare that to a liquid. The liquid state of matter. Liquid has definite volume. It will take on the shape of a container that you place it in. And just like a solid, it has particles that are close together, as you can see by this image here, but they're not arranged in a very ordered fashion. So they can actually slide past one another, which makes sense for a liquid. A gas. Gas has no definite shape or volume. It will expand to fill the volume and assume the shape of whatever container it's put in. And a gas consists of particles that are very far apart from each other, as you can see in this image here, and they move around randomly. So often you'll see the space in between the particles is greater than the size of the gas particles themselves. Okay, next concept, properties of matter. So we can consider different ways of classifying or characterising matter. We're going to consider here what are referred to as physical properties of matter and chemical properties of matter. Let's start with physical properties. Physical properties are those properties that can be observed or measured without changing the composition of the substance, that is, without changing the identity of the substance. These are physical changes that we can apply to substances: boiling, melting, solubility, and we can consider colour and odour. Now, we won't be talking about colour and odour. These are 2 properties that will be considered extensively by viticulture and winemaking students in their wine classes. But we will talk a lot more in later lectures about boiling point, melting point, and solubility. So, physical change. So still on physical properties, physical change will alter the substance or the material without changing its composition, without changing its identity. And a classic example is presented here for you to illustrate physical change. Let's consider this first image, solid water. So think about a block of ice. And if we apply a physical change to that block of ice, such as melting, then of course we end up with liquid water, but the particles of water are still exactly the same as the particles of water in the solid, in the block of ice. So we haven't actually chemically altered those particles. Then we can apply another physical change to the liquid water, for example, boiling. And if we boil the water, it changes to gaseous water, steam or water vapour. Again, the water particles themselves remain intact. So all we've actually done here is changed the state of matter. We've changed from a solid to liquid to a gas. So that's a really good way of thinking about physical change. Now let's consider chemical properties or chemical change. Chemical properties determine or describe how a substance can be converted into a different substance. So in this case, we're changing the identity of a particular substance. So chemical change involves a chemical reaction. And chemical reactions involve taking those particles that are joined together, breaking the bonds that join them together, rearranging the particles, and then reforming them into completely different substances. Here are some examples for you. A piece of paper burning. This represents a chemical change because when you burn paper, a lot of the carbon and hydrogen and oxygen that's found within the paper is released into the atmosphere. So for example, the carbon will combine with oxygen in the air to form carbon dioxide. So we're completely changing the nature of the substances within the paper. And of course, this type of reaction where you're burning something is called a combustion reaction. Now let's consider this second example, metabolizing an apple for energy. So when you eat an apple, the sugars in that apple are chemically modified by your cells. They're chemically modified, they're rearranged in such a way to form completely different substances that are no longer sugars, but those substances are used to provide energy that drives cell processes, whether we're talking about plants or animals. So again, chemical reactions must be occurring there. Third example, oxygen and hydrogen combining to form water. And this example is illustrated here. So these red spheres here represent two oxygens joined together. And that's how you would normally find oxygen in the atmosphere. The two white spheres represent two hydrogens joined together. And of course, that's how you find hydrogen in the atmosphere. Now, a chemical reaction is required to break those two red spheres apart, break the two hydrogens apart from each other, and then another chemical reaction is required to recombine one red oxygen with two white hydrogens to form a particle of water. So a really good illustration here of a chemical reaction occurring. All right, now let's move on to a different way of classifying matter. We can classify or categorise matter as either a pure substance or as a mixture. Let's start with pure substances. A pure substance is composed of a single component. It has a constant composition, regardless of the sample size, regardless of the origin of the sample. This is the important point here. Pure substance cannot be broken down to other pure substances by applying a physical change, such as boiling or melting. And some examples are shown here of pure substances: sugar, and these are particles of sugar, and water particles shown to the right. And we'll come back to pure substances in just a moment, but first let's visit the classification of matter as a mixture. A mixture is composed of more than one component, And the example shown here is sugar dissolved in water. It can have varying composition, so any combination of solid, liquid and gas, depending on the sample. But the important part of defining a mixture is that a mixture can be separated into its separate components by applying a physical change. For example, if you had sugar dissolved in water and you applied a physical change, for example, evaporating off all that water over time, you would separate the water from the sugar. Okay, so that's a true example of a mixture. Now let's go back to pure substances, because pure substances can be further broken down into two different classes: elements and compounds. So an element is a type of pure substance that cannot be broken down by a chemical change. Here we have an example of an element, pure aluminium metal. So it consists only of aluminium particles. And to the right, we have a compound. A compound is also a type of pure substance, but it's formed by chemically joining two or more elements together. And the example shown here is that of table salt, common table salt, which we call sodium chloride. This is the chemical symbol for sodium chloride. And shown here, we have sodium particles in grey and we have chloride particles in green. And they tend to love joining together to form salt. So that's an example of a compound. Now, it's interesting that elements, and we'll talk a lot more about elements next week, there's only about 118 elements known to man. Only about 118, and 4 of those were only discovered, or rather synthesised in the lab about 2 years ago. So that's all we know, about 118 elements. Compounds, on the other hand, we know of millions and millions of different compounds on Earth, whether they're naturally occurring or whether they're synthesised by scientists in the lab. All right, so let's now summarise this classification of matter. So matter is anything with mass and volume. Matter can be a mixture or it can be a substance, pure substance. A pure substance can be further subclassified as either a compound or an element. So a nice summary there for you. Moving on now, we're going to talk about measurement and the importance of units. So all students, regardless of your major, will end up measuring something, whether you're measuring growth of fish, whether you're measuring growth of algae in culture, or you're measuring plant yield, plant height, so on. There's always some sort of measurement that will take place. Or you're measuring the alcohol content in the wine that you're making, and so on. But important to note, every measurement is composed, of course, of a number and a unit. And the number itself is meaningless without the unit. So, for example, proper aspirin dosage is 325. Well, of course, that's useless, the number on its own, because we need to know whether it's milligrams or is it in pounds. Another example, fast time for the 100 metre dash equals 10. Again, the 10 is useless on its own without the appropriate unit. Now, as you know, in the US, they use the English system, which uses units like feet, gallons, pounds, and so on. But in just about every other country, every scientist and other professionals, they use the metric system. So units like metres, litres, and grams. And of course, the US is slowly coming around. They are slowly moving towards using the metric system. All right, each type of measurement in the metric system has what's called a base unit. Let's look at that. So the measurement of length, the metric base unit is the metre. and of course symbols are shown here to the right. Measurement of mass, the base unit is gram, for volume it's litre, and for time it's second. Now we're going to use this example of mass and the base unit of gram, just to illustrate what's meant by the base unit. All right, in this table we can see some prefixes, some which we commonly use, others which we don't. Prefixes such as mega, kilo, deci, centi, milli, micro, and we very rarely go down to the nano level. Micro, we do use this in some prac classes. Here's the symbol for micro, so this is a good one to keep in mind. All right, now remember we said that the base unit for mass is the gram. So let's think about how that relates to the use of these prefixes. Let's say you used this prefix, kilogram. Kilogram, what does kilo mean? Kilo means 1,000. So that tells you that 1 kilogram is 1,000 times greater than the base unit of gram. That makes sense because there's 1,000 grams in a kilogram. Let's say we used the prefix milligram. So the unit was milligram, and milli means thousandth. So that tells us, this prefix tells us that 1 milligram is 1,000th of the base unit of gram. In other words, there's 1,000 milligrams in 1 gram. So this just shows the relationship between the base unit of a given type of measurement and the prefixes that are used for metric units. All right, and here we have some conversions for you. So conversions for measuring length, conversions for measuring mass, and let's consider here the term mass in comparison to the term weight. We always use these two terms interchangeably and will continue to do so, but they actually have slightly different meanings. Mass is a measure of the amount of matter in an object. And this measurement doesn't change regardless of location. So if you measure the mass of something on Earth and you measure the mass of something on the moon, they will be identical. But weight, on the other hand, would change depending on location, because weight is the force that matter feels due to gravity. So think about that. If you weigh yourself on Earth and then you weigh yourself on the moon, you'll be much lighter on the moon because gravitational force is about 6 times less on the moon compared to Earth. Okay, so slightly different meanings, but as I said, we still use those terms interchangeably because in a practical sense, we use scales to weigh things. And here we have some conversion factors for volume. All right, our next concept relates to the concept of exact and inexact numbers. So what's an exact number? An exact number results from counting objects, or it's part of a definition. So for example, counting the fingers on your hands or counting your toes, you'll probably find exactly 10 fingers and exactly 10 toes, not 9.6 or 10.3, even though, of course, students tell me that that's possible. An exact number results as part of a definition. So here's an example of a definition. 1 metre equals 100 centimetres. Exactly 100 centimetres, not 99.8 or 100.2. So this is an exact number. We work mostly with inexact numbers. An inexact number results from a measurement, any type of measurement, or an observation. It always contains a certain degree of uncertainty. Let's look at some measurements. 15.3 centimetres, 1,000.8 grams. 0.0034 mil. They're all types of measurements, so they're all inexact numbers. And the reason they contain a certain degree of uncertainty relates to the type of instrument or the type of equipment that you're using to take the measurement. So, for example, if you were measuring an object that was 1 millimetre in length, imagine the difference in accuracy if you were using a 30 centimetre ruler to measure that object compared to a highly calibrated stage micrometer, which you would use with a microscope and measures accurately down to micrometers. Big difference in your final measurement. And so let's consider now what we refer to as the significant figures in your measurement. What do we mean by significant figures in your measurement? Significant figures are all the digits in your measured number, including one estimated digit, which is, of course, the last digit. All non-zero digits are always said to be significant. So in this example, 65.2 grams, there's no zeros in there, so all three of those digits are said to be significant figures. And of course, this 2 would be the estimated digit. And it's estimated because the actual correct measurement could actually be 65.1967, or it could be 65.23474. Okay, but obviously what we're using to take this measurement will only give us a certain degree of accuracy. Next example, 255.345 grams. There's no zeros there, so all those digits are said to be significant, including this one estimated digit, the 5. So six significant figures in that particular number there. All right, now when there's a 0 present, there are 2 rules, only 2 rules that you need to apply so that you know whether the zeros are counted as significant figures or not. So rule 1 states that a 0 counts as a significant figure when it occurs between 2 non-zero digits. In this example, 29.05 grams, the 0 is found between 2 non-zero digits, so it counts as a significant figure. So this number has 4 significant figures. 1.0087 mil, those zeros also occur between 2 non-zero digits, so they count as significant. So we have 5 significant figures. And of course the 7 is our estimated digit. Now, a 0 also counts as a significant figure when it occurs at the end of a number, and that number contains a decimal place somewhere. So we have a decimal in here. So these 2 zeros at the end count as being significant for a total of 5 significant figures. 620 with a decimal there, so this 0 also counts. So when doesn't a 0 count as significant? A 0 does not count as a significant figure when it occurs at the beginning of a number. So any zeros that occur at the beginning are not considered to be significant figures. This doesn't mean that you remove them. You can't remove them. They are there for a reason. They're simply fillers, place fillers. But they're not considered to be significant in terms of determining accuracy of your measurement. So these 3 zeros don't count. That means this number has 3 significant figures. These zeros don't count here, so we have 1 significant figure. A 0 also does not count when it's found at the end of a number that does not have a decimal anywhere within the number. So there's no decimal here, so we don't count that 0 as being significant. We have 3 significant figures. As I said, it doesn't mean we can remove the zeros. These zeros also don't count as significant because there's no decimal. Okay, and you'll be able to practice that in some of your tutorial exercises. All right, here are some rules for determining the number of significant figures that should be used in the answer when you're multiplying and dividing. And I'll let you look through these rules in your own time. So this is here just for your interest. And rules for rounding off numbers. Most students are familiar with these rules. I'll let you read through that. And rules for number of significant figures if you're adding or subtracting. They're quite straightforward. All right, and let's move on now to an important concept, the concept of scientific notation. This is one that I really want you to get your head around because it does come up quite a few times in later lectures, and it's also something that will come up in other subjects. Concept of scientific notation. So in any of the sciences, you'll come across really large numbers or really, really small numbers. So scientists devised this shorthand way of representing those numbers using what's called scientific notation. In scientific notation, a number is written as y multiplied by 10 to the power of x. Y is referred to as the coefficient, and this will be always a number between 1 and 10. X is referred to as the exponent, and it's any positive or negative whole number, but not a fraction. Keep that in mind for one of your tutorial questions. Not a fraction, has to be a whole number. All right, so let's look at some examples of scientific notation. And we're going to start with a standard number, 2,500, and we're going to convert this into scientific notation. First thing we do, step one, we move the decimal point to give a number between 1 and 10. Okay, so we would place the decimal point right here, and then we move that decimal point 1, 2, 3 places, place it in here, and that gives us the number 2.5 or 2.500. So we've got our number between 1 and 10. Then we multiply the result by 10 to the x. So we write out 2.5 multiplied by 10 to the x. Now, x will be, the number for x is simply the number of places that you moved that decimal point. So remember, we moved it 1, 2, 3. So x, or the exponent, becomes 3. Because we moved that decimal to the left, then x is a positive number. And there we have our number written in scientific notation. 2,500 becomes 2.5 by 10 to the power of 3. All right, not much of a shorthand method if you ask me, but just a simple illustration of how to apply the concept of scientific notation. All right, let's look at another example. 0.036. To convert this to scientific notation, we follow the same rules. First, we move the decimal point to give a number between 1 and 10. So we're going to take that decimal there and move it 2 places. Once we place it there, that gives us the number between 1 and 10 of 3.6. So then you would write 3.6 multiplied by 10 to the x. So now you just have to work out what that x is. Again, you look at how many places you moved the decimal point. We moved it 2 places, but because we moved it to the right, that x will be a negative number. So instead of just 2, we write -2. So 0.036 written in scientific notation is 3.6 by 10 to the power of -2. How's everyone going? Is everyone following this okay? Yes, terrific. Excellent. And you will get some practice once again, in your tutorial questions. All right, another couple of examples, but this time, rather than going from a whole number to scientific notation, we're going to go from a number written in scientific notation to a whole number. All right, so we're given this number here, 2.800 by 10 raised to the power of 2. So this 2 here tells us how many places to move the decimal. It's a positive number. That means we move the decimal that many places to the right. Here's the decimal, move it 1, 2 places to the right, put it in here, and that gives us the whole number of 280.0. Let's look at another example, and in this case the exponent x is a negative number. You can see there we've got -2, so that tells us we have to move the decimal point to the left. There's our decimal, 1, 2, place the decimal here and pop a 0 in this place here. That will give us the whole number 0.0280, as you can see here to the right. Okay, so do some practice, make sure you understand that, because this is an important concept going forward. And of course, when I say that, I normally mean it's an important concept also for your exams. All right, occasionally you'll have to convert a number which is using 1 unit into a different unit. To do this, we use conversion factors, which is a term that converts a quantity in 1 unit to a quantity in another unit. To apply these conversion factors, we take the original quantity that you've been given, multiply it by the conversion factor to give the desired quantity using the desired unit. Now, you'll have to do this only on occasion. For viticulture and winemaking students, you will have to do this also in wine chemistry next year or in your second year. All right, conversion factors. So what are the conversion factors? Conversion factors are usually written as equalities. Here's an example of an equality. 2.21 pounds equals 1 kilo. That's our equality. That's our conversion factor if we were converting from a number in pounds to kilos, or vice versa. Now, in order to use this conversion factor, we need to express it as a fraction. We need to write it as a fraction. So that's pretty simple. We just put 1 on top of the other. So, for example, 2.21 pounds over 1 kilo. Or do we write it the other way? Do we write 1 kilo over 2.21 pounds? Well, that depends on the problem. Let's look at an example for that. Here we go. And by the way, this is called the factor label method, this method of converting. A really nice, simple method that you should learn. All right, here's our example. 130 pounds, this is our original quantity, and we need to convert that to kilograms. So what's the conversion factor for pounds to kilos? Here it is, the conversion factor already expressed as a fraction. Do we use this one here, or do we express the conversion factor like this? Well, that depends on the unit that you're trying to get rid of and the unit that you're trying to convert to. So in this case, we want to get rid of the pounds and we want to convert to kilos. So make sure you select the fraction where the desired unit is at the top. So a desired unit of kilogram is at the top, and the unit that you're trying to convert from is at the bottom of the fraction. So we want to get rid of pounds. So if we use this particular conversion factor, then we can cancel the pounds here with each other, and that leaves us with our desired unit of kilograms. And then we can simply do the math there. 130 multiplied by 1 divided by 2.21, and that should give you 59 kilograms. So pretty straightforward factor label method. Very nice method. Let's look at one more example. How many grams of aspirin are found in a 325 milligram tablet? Identify the original quantity and the desired quantity, and always include units. Remember, any number should include units. Remember that right through your studies. Original quantity, 325 milligrams. Desired is grams. Write out the conversion factor that you need to solve the problem. In this case, 1 gram equals 1,000 milligrams. Then write that as a fraction. This fraction or that fraction. And then decide which unit you want to keep. We want to keep grams, so make sure it's at the top. And we want to convert from milligrams, so we want to get rid of this one, make sure it's at the bottom of the fraction so we can cancel it out. Then set up the problem as such, cancel out milligram with milligram and solve the problem. So the answer is 0.325 grams. All right, second last concept for the lecture, and this one involves temperature. There are 3 temperature scales that are used: degrees Fahrenheit, degrees Celsius, and a third one called Kelvin. Note that we don't say degrees Kelvin, we just say Kelvin. Here are the conversion factors shown here to convert from degrees Celsius to Fahrenheit, from Fahrenheit to Celsius, and so on. The most important one that I want you to learn and remember is how you convert from degrees Celsius to Kelvin, because you'll need to do this later on in other lectures. So if you were given a temperature in degrees Celsius, you simply add that to this number, 273. Add them together and that will give you the temperature in Kelvin. So a really simple one, really simple conversion. All right, let's look at the 3 temperature scales. We've got Fahrenheit, Celsius and Kelvin scale. Let's start here, Celsius, and we're all familiar with the boiling point of water, 100 degrees Celsius. On the Fahrenheit scale, that equates to 212 degrees Fahrenheit. On the Kelvin scale, 373 Kelvin. Moving down here to the freezing point of water, 0 degrees Celsius, 32 degrees Fahrenheit, and 273 Kelvin. So if we look at the difference between the freezing point of water on the Celsius scale and the boiling point, the difference is 100 degrees Celsius. Let's compare that to the Kelvin scale. Freezing point of water here, boiling point of water up there, a difference of 100 Kelvin. So that tells us that 1 degree Celsius is exactly the same size as 1 Kelvin. This is not the case for the Fahrenheit scale. Look at the difference between freezing point of water here, 32 Fahrenheit, and boiling point 212 degrees Fahrenheit. That's a difference of 180 degrees Fahrenheit. So 1 Fahrenheit is not the same in size as 1 Celsius or 1 Kelvin. All right, one more point on this slide, and that relates to this term here, absolute zero. Absolute zero occurs at minus 273 degrees Celsius, minus 460 degrees Fahrenheit, and 0 Kelvin. So this is why the Kelvin scale was first established, because absolute zero is thought to be the coldest possible temperature. This is the temperature at which all molecular motion ceases completely. So all particles will stop moving, and if there's no movement, there cannot be any heat generated. So that's the definition basically of absolute zero. 0 Kelvin represents absolute zero. All right, our final concept involves that of dilution. A very important one for some of you, to be able to dilute a solution and come up with exactly the right concentration that's required. Now, this is a concept that's actually introduced later in semester in a bit more detail, but I like to start off semester introducing one of only a few formulas that we use and only a few formulas that you tend to find handy in your study and in your chosen major. And this way that you can start getting a bit of practice with using formulas and understanding how to rearrange formulas. All right, dilution is obviously the addition of solvent, such as water, for example, to decrease the concentration of the solute. In doing this, the solution volume changes, but the amount of solute is constant. So, for example, here's our initial solution, and we have so many particles of solute in there, which gives us a particular concentration. And if we dilute that solution with additional water, for example, which will be our solvent, then the volume increases, but the number of particles remains the same. So, of course, the concentration will change. Now, to work out dilutions, we use this very useful formula here called C1V1 equals C2V2. Let's look at what this means. C1 is the concentration of your initial solution. V1 is the volume of your initial solution. C2 and V2 represents the concentration and volume of your final diluted solution. So let's work this formula using an example. Here's the question, and as I always say to students, half of the battle in answering questions is to interpret the question correctly. So really read the question, focus on what the question is asking, so you interpret the question correctly. What is the concentration of a solution formed by diluting 100 ml of a 5% salt solution to 200 ml? All right, look at that again. What is the concentration of a solution formed by diluting 100 ml of a 5% salt solution to 200 ml? So if you're reading that question correctly, you will see that we're actually starting with a 5% solution, 100 ml of a 5% solution. So that's your initial solution here. In other words, your initial concentration is 5% and your initial volume is 100 ml. We're going to dilute that to a 200 ml final solution. 200 ml, so that's your V2. V2 is 200 ml. That leaves us with our unknown. C2 is our unknown, and of course that's what the question's asking. It's asking what the concentration of that final solution will be after you've diluted it out to 200 ml. All right, so first step is to think along those lines and identify your unknown. Which value are you trying to solve for? That's half the battle. Then we can write it out in this way. C1 equals 5%, V1 equals 100 ml, C2 is our unknown, V2 is 200 ml. Then the final slightly tricky bit, until you get used to it after a bit of practice, is to rearrange the formula so that you can solve for the unknown. And I'm going to use my pencil just to illustrate this. All right, so if we had C1, V1 equals C2, V2, and we've identified that C2 is our unknown. Okay, that's what we're trying to solve for. Identify your unknown and then leave it exactly where it is. Leave it there and move this one that's next to it. Move this. It's the easiest way to do it, and place it under the other side. Place it under here. Draw a line and write V2. Now, once you've done that, you've actually isolated your unknown on one side of the equation, and that makes it very easy to solve. So this is in reverse. I don't like equations in reverse. I'm going to rewrite it. C2, so we've got C2, our unknown, equals C1 multiplied by V1. In other words, 5% multiplied by 100 mil divided by V2, which is 200 mil. And once you've done that, it's very easy then to solve the problem. 5% multiplied by 100 mil and then divide that by 200 mil, and you should come up with 2.5%. Okay, now before you actually calculate the answer, look at the numbers that you've got in that equation and look for any like units. For example, we have mil here and we have mil here, so we cancel them out. They cancel each other out, and that leaves us with this unit here, percentage, which is the concentration that we're using. We're left with this unit. What are we trying to solve for? We're trying to solve for concentration. We can see it there, we could see it there, so we know we're on the right track when the remaining unit after cancelling out like units is what we're trying to solve for. So that's a good habit to get into. So let me just clear that, and we will do one more example after I get rid of my pen. All right, final example. How many mil of a 2.5% salt solution would be needed to prepare 25 mil of a 1% solution? So remember, read the question carefully, interpret the question. Work out what C1, V1, C2, V2 actually is. So C1, our initial concentration is 2.5% because we're told that we've got a 2.5% salt solution. V1, we don't know. That's our unknown because we're asked how many mil of this 2.5% salt solution, how many mil do we need to prepare a 1% solution in a total volume of 25 mil. Okay, so we've got that all organised. Now remember how to rearrange this so that you isolate your unknown on one side of the equation. Leave the unknown there, then take the value that's next to it, which is this one, and put this under the other side. Okay, let me draw this just to make sure. Okay, so I'm going to put an equal in there to represent the formula. Here's our unknown. Leave that exactly where it is. Take this one, draw a line under the other side and move it over here. So put your 2.5% under this side of the equation. Then all you have to do is solve the equation once we set it up. But before we solve it, remember, look for like units. So we've got percentage here and percentage up there. So we can cross them out. What does that leave us with? The unit of mil. What are we trying to solve for? Volume. So we're on the right track. And then you just work your way through that, and the answer is 10 mil. And that concludes our lecture. Well done, everyone. How are you feeling? I like like that. Very informed. That's very good. That's good to hear. So far good, terrific. That's what I like to hear. And we finished in good time, which is great. All right, fantastic, guys. Well done. Have you got any questions for me? And while you're thinking, I'd just like to pull up the your homework for this week. Oops, let me get rid of those annotations. Clear. Here. All right, so here's your homework for this week. Tutorial exercises. You'll find this on Moodle under the week 1, in the week 1 block. Tutorial questions. This set of questions is assessed. It is due by next Monday, by 6 p.m. next Monday. The assessment weighting for these questions is 4%. So you remember, you could look at these questions on Moodle and work your way through them. And then to actually submit your answers, you do this via the relevant online quiz. Also on Moodle under the assessments heading. Okay, everyone happy with that? Remember, if you've got any questions at all, if you're going through these tutorial questions and one is really bugging you, or one or more, hopefully it's not all of them, feel free to drop me an email or call me if you like. It's up to you. Anytime on Tuesday morning is good. Actually, all day Tuesday, but week 3 I start teaching Tuesday afternoon. Wednesday anytime. There are a few days where I'm teaching all day on a Wednesday, and Thursday, most Thursdays are good also. Not Friday. Fridays I'm normally at La Trobe, so you won't catch me on a Friday. But if you do, if I'm not in my office and you call, please leave a message and I will get back to you. Just leave me with your best contact number, mobile number or whatever. Any other questions? You're welcome. Thank you, everyone. Thank you very much, and I'll see you next week. Yes, you too. Good night.